Hello, professor and classmates. Today, the group number 4, made up by Astrid Rivera, Geisen Garcia, Denise Silva, and I, Yoan Verjans, have the pleasure of presenting our final course presentation. Introduction. Overview of airline operation. As is well known, airline operations today represents a complex and sophisticated structure that goes far beyond cargo or passengers transportation. This sector is essential for the global economy and tourism. For this reason, it depends on precise coordination between multiple elements, from fleet management, aircraft maintenance, and air traffic control to route optimization, logistics, supplies, and operational security. Furthermore, the necessity to adapt to changing demands, follow tight international rules, and reduce environmental effects adds an additional level of challenge and responsibility. Understanding the complexity behind each flight demonstrates not just the sector importance, but also the ability of aviation to evolve and innovate in an environment of high competitiveness and growing demand. The second point is the project scope. In this project, we will explore the essential components of airlines operations that are fundamental to safe and efficient airline management. 14 CFR Part 121 regulations. This this section covers the operational requirements established by the FAA for commercial airlines, including safety protocols, maintenance, and crew requirements. Meteorology applications. Weather plays a significant role in flight safety, requiring robust forecasting and planning to avoid hazards and optimize routes. MEL and CDL performance. Essential for management aircraft functionality while adhering to safety standards. The MEL and CDL systems allow operation under certain non-critical equipment failures. NOTAMs and the National Airspace System (NAS). The importance of notice to air missions (NOTAMs) and understanding of the NAS are vital for navigating controlled airspace, enabling the pilots to stay informed on temporary airspace hazards or restrictions. IFR chart application. Instrument Flight Rule (IFR) charts are used to guide flights in poor visibility and congested airspace, ensuring the safe passage through controlled zones. IFR route optimization. Optimization of IFR routes ensures fuel efficiency, minimizes delays, and reduces operational costs, crucial for economic and environmental goals. Weight and balance. Maintaining proper weight and balance is crucial for the flight performance, affecting the fuel burn, takeoff, and landing calculation. The human factors. Recognizing the influence of human factors in aviation helps mitigate risk associated with human errors and enhance crew resource management. NAT, high-level airspace. The North Atlantic high-level airspace governs transatlantic routes with specific procedural standards essential for maintaining safety over international waters. ETOPS. Extend Range Twin-Engine Operational Performance Standards. These standards permit twin-engine aircraft to operate over remote areas, expanding the route flexibility while ensuring the safety of the flight. Objective statement. The primary objective of this project is to provide a comprehensive understanding of the fundamental systems, regulation, and process that govern airlines operation. This includes analyzing the interconnected roles of each topic area and demonstrating how they contribute to the airline's ability to operate safely and efficiently in both domestic and international airspace. 14 CFR Part 121 Regulation. Overview of Part 121. Part 121 of Title 14 of the Code of Federal Regulation (CFR) defines the standards and regulatory requirements for commercial air transport operated by U.S. certificate carriers. This regulation, published by the Federal Aviation Administration (FAA), applies to airlines that provide scheduled passengers and cargo service, ensuring that these operations adhere to the highest safety requirements. Part 121 regulations cover a wide range of criteria, including aircraft maintenance practice, crew training requirements, and operational control standards. Part 121, by prescribing certain rules, plays an important role in improving commercial air transport safety, reliability, and uniformity. Key regulatory areas. 14 CFR Part 121 covers several essential regulatory areas critical to maintain safe and efficient airline operations. Crew training. Part 121 requires rigorous training for pilots, flight attendants, and other crew members, including emergency procedures, aircraft systems, and crew resource management. Recurrent training is required on a frequent basis to maintain a staff proficient in their jobs. Aircraft maintenance. Comprehensive maintenance requirements guarantee that airplanes are airworthy. Part 121 prescribes the frequency and breadth of inspections, maintenance procedures, and record keeping that airlines must implement to maintain compliance and aircraft reliability. Operational controls. Airlines operating under Part 121 must maintain strict operational controls over flights. This includes dispatching procedures, monitoring flight progress, and ensuring that safety requirements are met throughout the flight. Dispatchers played a vital role in coordinating with pilots, monitoring weather conditions, and handling in-flight issues. Emergency procedures and passenger safety. The regulation requires airlines to establish protocols for various emergency scenarios, including medical emergencies, evacuation, and cabin decompression. This includes passenger safety briefings and emergency equipment inspections. Compliance strategies. Airlines employ various strategies to comply with Part 121 regulations. For example, Safety Management System. Safety management system frameworks help airlines proactively manage risk, identify potential hazards, and develop mitigation strategies. The FAA mandates safety management system program for Part 121 operators, which enable continuous monitoring and enhancement of safety practice. Training and documentation. Airlines invest heavily in recurrent training programs to ensure that employees remain proficient and compliant with regulatory requirements. Detailed documentation is maintained for demonstrate compliance, which is regularly reviewed by the FAA. Technology and automation. Airlines utilize advanced software systems to manage compliance with Part 121, especially in areas like maintenance, crew scheduling, and operational control. These tools streamline process, improve data accuracy, and facilitate real-time monitoring. Non-compliance with Part 121 regulation can result in serious consequences such as fine, penalties, grounding of aircraft, or even suspension of an airline's operating certificate. The FAA conducts regular inspections and audits to ensure that airlines maintain compliance, and violations are often met with enforcement actions to maintain industry standards. Case studies: Colgan Air Flight 3407 in 2009. This tragic incident involved the crash of Colgan Air Flight 3407 due to pilot error, led to increased scrutiny on crew training and fatigue management. The aftermath resulted in more stringent Part 121 regulations, requiring additional training hours for pilots and stricter rest requirements, known as the Flight 1500 rule. Alaska Airlines. Alaska Airlines faced penalties after a crash due to inadequate maintenance procedures. Subsequent investigation highlighted lapses in their Part 121 compliant maintenance program. The airline implemented more stringent compliance checks and enhanced maintenance protocols to avoid future incidents. Meteorology applications. Importance of meteorology in aviation. Meteorology is crucial in aviation because the weather directly influences every stage of flight operations. Adverse weather conditions can significantly impact some factors like flight safety and fuel efficiency. Weather affects both pre-flight planning and in-flight adjustment. Airlines and pilots rely on accurate, up-to-date weather data to make decisions about flight paths, altitude adjustments, speed, and even whether a flight can be conducted safely. The weather can affect the flight through several factors, such as strong winds that affect the flight time and fuel consumption, storms or turbulence that affect the flight safety of the airplane, and generally it is sought to draw another route to avoid it and ice that can freeze certain parts essential for control of the plane, reducing maneuvering. Weather data source in aviation. Airlines use various tools and sources to gather and interpret meteorological data, helping pilots and dispatchers to make informed decisions. Some of the main data sources include METAR, Meteorological Aerodrome Report, a routine hourly report providing current conditions at an airport, such as temperature, humidity, wind speed, cloud cover, and visibility. Metadata helps pilots understand the immediate conditions at their departure and arrival airports. TAF, Terminal Aerodrome Forecast. A forecast used every 6 hours for airports, predicting weather for a specific period, typically 24 to 30 hours. TAF provide insight into upcoming conditions, including potential storms, changes in wind speed and visibility, which influence flight planning and fuel management. SIGMET and AirMet. SIGMET's significant meteorological information and AirMet's meteorological information provide real-time information on severe weather conditions like turbulence, icing, and storms, which are critical for in-flight safety. The last one is PIREPS, pilot reports. Reports from other pilots about observed weather conditions, which can supplement official data and provide real-time insight into weather en route. Application in flight planning. Flight planning incorporates weather data to optimize safety, efficiency, and passenger comfort. Airlines and flight dispatchers use meteorological data to select flight routes, determine optimal cruising altitudes, and calculate necessary fuel loads. During planning and decision process, pilots and dispatchers will consider the following factors. Route optimization. Pilots avoid routes with severe weather by choosing alternative paths with better conditions, which save time and fuel. Fuel management. Weather forecasts help estimate the amount of fuel needed to the trip, including additional fuel to accommodate potential delays or rerouting due to adverse weather. Altitude selection. Pilots choose altitudes to avoid turbulent zones or to minimize headwinds and maximize tailwinds, making the flight more efficient and comfortable. Case study. One notable case where weather played a critical role in flight operation was the Air France Flight 447 disaster in 2009. The aircraft encountered severe thunderstorms over the Atlantic Ocean, leading to a series of events that ultimately caused the plane to crash. The investigations revealed that the pilots struggled to handle the unexpected weather conditions, highlighting the importance of accurate weather forecasts and proper training in dealing with adverse weather. MEL and CDL performance. Minimum Equipment List MEL. The Minimum Equipment List is a regulatory document that identifies a specific equipment that may be allowed to remain inoperative on an aircraft without affecting safety. Customized for each aircraft type, the MEL provides guidance on which systems, instruments, and equipment can be deferred if they aren't essential for safe operation under certain conditions. Each item listed in the MEL includes restriction, maintenance actions, or operative procedures that must be adhered to when the equipment is inoperative. The MEL's purpose is to ensure continued safety while offering operational flexibility, helping to reduce delays and cancellations due to the minor equipment issues. Configuration Deviation List (CDL). The Configuration Deviation List identifies external parts of an aircraft that can be missing without compromising the navigability or put in risk the safety of the flight. The CDL is prepared by the aircraft manufacturer and approved by the state of design. It includes information on any operating limitation and performance correction associated with missing parts. However, the CDL will typically include performance penalties associated with missing items, such as increased drag or reduced fuel efficiency. Each CDL item lists the permissible deviation, any requirement compensatory measures, example increase the fuel load, and any performance adjustment. Performance considerations. Both MEL and CDL items can have a significant impact on aircraft performance, particularly in terms of fuel consumption, weight, and balance. MEL items can influence systems like engines, navigation, and electrical systems, thereby affecting the fuel efficiency. CDL items, on the other hand, can change the aircraft aerodynamics, resulting in increased drag or reduced climb rates. When MEL items affect components such as anti-ice systems, hydraulic system, or certain flight controls, it may restrict the aircraft operational capabilities, potentially limitation operations in adverse weather or increased fuel usage. CDL items such as missing fairings or control surface panels can increase drag, which impacts in fuel consumption. This might require the crew to plan for additional fuel reserve or reduce the payload. Operational examples of MEL and CDL impact on flights. MEL example. In operative weather radar, a flight A flight crew finds the weather radar inoperative before departure. According to the MEL, the radar can be deferred, but only if the flight will avoid the areas of known or forecasted adverse weather. The crew adjusts their route to avoid thunderstorms, ensuring passengers' safety while still completing the flight. CDL example. Missing a winglet. A small winglet is missing from an aircraft, a condition that is listed as permissible in the CDL. However, the missing winglet increased drag, affecting the fuel efficiency. The flight crew compensates by planning for additional fuel to cover the increased fuel burn due to the drag.
Hi, this is Astrid speaking, and I'll be discussing the topics of NOTAMs, the National Airspace System, IFR charts, and IFR route. Let's start with NOTAMs. NOTAMs are one of the most critical tools in aviation that ensures safety and efficiency in flight operations worldwide. Whether you're a pilot, air traffic controller, or aviation enthusiast, understanding NOTAMs is essential. Let's start with the basics. What is a NOTAM? A NOTAM is short for Notice to Airmen. These are time critical aeronautical information, either temporary in nature or not sufficiently known in advance to allow publication on aeronautical charts or in operational publications. NOTAMs are distributed globally and are standardized by the International Civil Aviation Organization, mostly known as ICAO, ensuring that pilots and operators receive consistent and clear information. For instance, an NOTAM could inform a pilot about temporary runway closure, the presence of obstacles like construction cranes near an airport, or airspace restrictions due to events such as air shows or military exercises. Without NOTAMs, pilots might unknowingly encounter unexpected hazards, putting their safety and their passengers' safety at risk. The purpose of NOTAMs is simple but vital. Prevent hazards by informing pilots of obstacles or conditions that could affect their flight. Optimize operations by providing updates on closures, temporary restrictions, or new procedures. And facilitate the decision making by helping crews plan routes and manage risk effectively. NOTAMs cover a wide range of information and is generally classified into four categories based on their purpose and urgency. Let's start with NOTAMs D. These include information about taxiway closures, personnel and equipment near or crossing runways, and airport lining aids that do not affect instrument approach criteria, such as visual approach stop indicator. All the NOTAMs are required to have one keyword as the first part of the text. Then we have NOTAM FDC, Flight Data Center. They are issued for regulatory changes such as temporary flight restrictions or amendments to instrument approach procedures. International NOTAMs provide updates on international airspace and global navigation aids, crucial for cross-border operations. And last but not least, we have military NOTAMs that are specific to military. Now let's dive into the structure of NOTAMs. At first, we have an exclamation point followed by the accountability location identifier, that is the location that keeps track of NOTAM numbering, and it can be an airport, flight data center, or other location. In this case, we are talking about the Orlando International Airport. After that comes the NOTAM number that has a 2-digit number month, in this case 11, that is November, and a 3-digit number ranging from 001 to 999. Then we have the location identifier, that is the ICAO code of the facility or location that is affected. In this case, we have MCO, that is the code for the Orlando International Airport. After that comes the keyword that helps identify the type of information in a NOTAM. In this case, we are talking about the airport apron, that is the designated area where aircraft park, loaded, unloaded, refueled, and boarded by passengers. After that comes the attribute activity or surface designator, that is really a when needed component. In this case, it says that not all the apron has this condition, but just like a segment that says airside 2 ramp between taxiway Juliet 5 and taxiway Hotel 2. Then we have the condition or description of the problem that provides detailed information such as runway closures, obstructions, or changes in procedures. In this case, it says edge marking not standard. The edge markings are painted lines that delineate the boundaries of the ramp, and it says that are not standard, which can mean that they are faded or improper. Then we have the validity period that indicates the time where the NOTAM starts and when it ends. It's a 10-digit number date time group and it's in UTC. The first 2 digits are the year, the second 2 digits are the month. Then it's followed by 2 digits day, 2 digits that are the hour, and the last 2 digits are minutes. In this case, it says that the start time is the 21st of November of 2024 and it starts at 14:56, and the end time is March 31st of 2025 at 2200 UTC. Now let's read it all together. It says that at the Orlando International Airport, the edge marking between taxiway Juliet 5 and taxiway Hotel 2 on the airside 2 ramp of the apron area are not standard, and this NOTAM starts at November 21st of 2024 at 14:56 UTC to March 31st, 2025 at 2200 UTC. To March 31st, 2025, and it ends at 2200. Now we have another example. Let's decode it a little more faster. At first, we have the accountability location identifier that it says DEN, that is the Denver International Airport. Following this, we have the NOTAM number that it says 11, that indicates that it was issued in November, and then this 776, that is the sequence number for that month. After that, we have the location identifier that is the Denver International Airport. Following this, we have the keyword that it says runway, and then we have the surface designator that it says that is runway 35 right. After that, we have the condition that says ALS, that is referring to the approach lighting system, and it says US, that it means unserviceable or out of service. And following this, we have the validity period that says that it starts on November 22nd of 2024 at 1600 UTC, and the end time is November 22 of 2024 at 1900 UTC. Let's switch our attention to the National Airspace System, the framework within which the NOTAMs operate. The NAS is a complex interconnected system that includes all airspace, airports, air navigation facility, and associated services within the United States. Its primary goal is to ensure the safe and efficient movement of aircraft. The NAS is supported by ground-based infrastructure such as radar systems and navigation aids, as well as a satellite system like GPS, ensuring seamless communication and navigation for all air traffic. Functions of the National Airspace System. Safe air traffic management. The NAS ensures that aircraft are safely managed and separated in the air and on the ground, preventing collisions and optimizing the flow of traffic. Efficient routing. The system helps determine the most efficient flight paths for aircraft, balancing traffic load and minimizing delays. National and international coordination. The NAS is interconnected with the international airspace system, coordinating U.S. air traffic with global aviation operations. Adaptability to different types of aircraft. It supports various aircraft types, from general aviation small planes to large commercial airliners and military aircraft. Now let's see how does NAS work. Step 1, pre-flight. Pilots file a flight plan with the air traffic controller and get weather information and wait for clearance for taxi. The plane won't taxi until a ground controller, that is the one keeping track of all the airplanes over the airport, says it's okay to taxi. That controller will direct the plane along taxiways to the runway where the local controller takes over. Step 2, takeoff. Local controller will guide the plane through takeoff and over set course just beyond the airport boundaries. After takeoff, control is handed to TRACON, Terminal Radar Approach Control. These controllers keep planes separated within 50 miles of an airport's airspace at altitudes up to 17,000 feet. Step 3, en route. High altitude flights are managed by Air Route Traffic Control Center, ensuring safe distances between planes. Radar and ADS-B track aircraft position in real time. Step 4, approach. As the airplane is near its destination, TRACON guides it down towards the runway, and ATC keeps vectored for descent and approach. Step 5, landing. After the local controller takes over for landing, the ground controller clears the plane to land and guides it to the gate. The NAS ensures safe and efficient air travel through coordinated communication, tracking, and traffic management. NOTAMs and the NAS form a crucial partnership in modern aviation. NOTAMs keep pilots informed about immediate hazards and operational changes, while the NAS provides the infrastructure to manage air traffic efficiently. Together, they exemplify the meticulous planning and coordination required to maintain the safety and reliability of our skies. Now let's talk about one of the fundamental aspects of aviation, airspaces. What is airspace? Airspace refers to a specific area in the sky that are designated for particular uses and regulated by aviation authorities. The way airspace is structured impacts everything from where you can fly to, how you can fly there, and whether you need to communicate with ATC. The classification of airspaces varies depending on traffic volume, safety concerns, and other operational needs. Let's break it down into three main types of airspace: control, uncontrolled, and special use airspace. Control airspace is the portion of the sky where ATC provides service to aircraft. This is the most structured and regulated type of airspace, designed to maintain safe distances between aircraft and manage traffic flow efficiently. Key points about control airspace is that aircraft in control airspace are generally required to communicate with ATC, and they must follow specific flight rules. Control airspace is divided into five classes: A, B, C, D, and E, each with its own set of rules for entry, altitude requirements, and communication protocols. Class A is the highest level of controlled airspace, typically from 18,000 feet above sea level to flight level of 60,000 feet, where pilots must be on IFR flight plan and in consistent communication with ATC. On IFR charts, it appears with a thick blue line. Class B, near busy airports such as LA or Chicago, where all aircraft must receive ATC clearance to enter. And it appears on the IFR chart by a blue solid line. Then we have Class C and Class D that are surrounding airports where pilots need to communicate with ATC but do not need explicit permission to enter. These are represented in the IFR chart by a blue dash or solid lines. Then we have Class E that begins at 1200 feet above ground level in most areas and extends up to 1800 feet above sea level. It appears at the IFR en route chart as a shaded light blue or magenta. Now let's continue with uncontrolled airspaces. In this, we only have one that is Class G, that is low altitude areas, often in rural or remote regions, and does not require ATC services. Pilots are responsible for their own separation from other aircraft. Then we have the special use airspaces, starting with the prohibited areas that flight there is absolutely prohibited, such as around sensitive government sites or military installations. In the IFR en route charts, these are marked with a bold blue line and labeled with a P. Then we have the restricted areas that are areas where flight is restricted due to military or hazardous activities. Aircraft must have permission to enter. On the IFR charts, these are also marked with bold blue lines and labeled with an R. Then we have the warning areas that are marked with brown or yellow shaded regions, and these are offshore zones with potentially hazardous activities. Then we have military operations areas that separates military training from IFR traffic. Let's talk a little about IFR charts, starting with IFR en route charts. These are a critical tool for pilots operating under instrument flight rules. These charts provide the necessary information for navigating between airports, ensuring safety, efficiency, and compliance with airspace regulations. They depict routes, navigation aids, airspace structure, and other essential data required for en route flight. The primary purpose of IFR en route charts is to assist pilots in navigating the controlled and uncontrolled airspace along their planned route. IFR charts are important because they provide critical information for avoiding obstacles, maintaining safe separation from terrain and other aircraft, offer standardized routes and procedures to minimize delays and optimize air traffic flow, and ensure adherence to airspace regulations and ATC instructions. Now let's see some of the key components on IFR en route charts. Let's start with airports. Airports on IFR en route charts are depicted using standardized symbols and colors. As you can see in the slide, I put a little legend that has different symbols that represent the different types of airports. Also, they have different color coding. Blue airports have approved U.S. Department of Defense low altitude approach. Green airports are any airport with an approach, and brown airports are airports without a published instrument approach procedure. Also, each airport symbol on an IFR en route chart is accompanied by additional information that helps pilots determine its suitability for their route and operations. This includes the name and locations. Airports are labeled with their name and location identifier, the ICAO location indicator, making them easy to locate and identify. Also, they give us the elevation of the airport measured in feet above mean sea level, that is often shown to help pilots account for terrain and altimeter settings during approach or departure. They also give us the length of the longest runway, crucial for determining whether the airport can accommodate the aircraft performance requirements. Lighting information, runway lighting capabilities are indicators such as L for lighting available, or they have an L in italics for lighting that is pilot controlled or part time. Also, they have some services that may include additional notes about availability of fuel or other services marked by symbols or annotations, and instrument approach types that airports with a specific instrument approach, such as ILS, RNAV, or BOR approaches, are included, making them more reliable for IFR operations. Navigation aids are one of the most important components of IFR and route charts. They serve as the backbone of air navigation, providing the data and signals required for accurate positioning and routing. Pilots relied on navids to plan and execute routes, determine fixes, and ensure safety during IFR operations. What are navids? Navids are ground-based systems that emit signals pilots use for navigation. These aids guide aircraft along designated routes, help define airways and intersections, and support approaches and departures. Types of navids. We have the VOR, very high frequency omnidirectional range, that provides 360-degree radials for navigation, enabling pilots to determine their position relative to the station. They are represented as an hexagon, black hexagon, and includes the identifier, that is a three-letter code, frequency, and mode Morse code signal. Then we have the VOR DME, distance measuring equipment, that combines VOR's directional guidance with DME's distance information. It's the same symbol as the VOR but with a small box labeled DME, and the distance to the station measured in nautical miles. Then we have the tactical air navigation symbol on IFR charts, that is depicted as a three-sided triangle, often black or bolded. Is a unique symbol that represents its military specific nature, providing both azimuth, that is direction, and distance information for navigation. Then we have the DME only station, that is represented as a square box, and in this case a standalone DME transponder. Ways depicted on IFR and route charts are structured routes that facilitate efficient and safe navigation for aircraft operating under instrument flight rules. These airways are categorized based on altitude and navigation methods, each serving specific operational needs. We have the Victor Airways, that are low altitude airways designated for IFR operations below 18,000 feet mean sea level. They are identified by a V followed by a route number and are depicted on the chart in black. These airways are based on BOR or BORTEC navigation aids. They provide structured routes for aircraft operating at lower altitudes, ensuring separation from terrain and other air traffic. Then we have jet routes, that are high altitude airways designated for IFR operations at or above 18,000 feet mean sea level. They are identified by a J followed by a route number. On the chart are depicted in black and these routes are primarily based on BOR or VORTAC stations. They facilitate efficient routing for aircraft operating at higher altitudes, optimizing fuel consumption and airspace management. Then we have RNAV routes that allow aircraft to navigate between any 2 points without relying solely on ground-based navigation aids. There are two types, T routes and Q routes. T routes are low altitude RNAV routes identified by a T followed by a route number, and they are depicted in blue on IFR and route low altitude charts. Q routes are high altitude RNAV routes identified by a Q followed by a route number, and they are depicted in blue on IFR and route high altitude charts. These routes utilize GPS or other RNAV capable system and offer greater flexibility in flight planning and can reduce congestion on traditional airways. Altitude constraints in aviation refers to specific regulations or limitations regarding the altitude at which an aircraft must fly during different phases of flight. These constraints are essential for maintaining safe separation between aircraft, ensuring obstacle clearance, and optimizing navigation. In IFR flight planning, there are three key altitudes that are crucial for ensuring obstacle clearance and maintaining safe flight paths. The minimum en route altitude, the minimum en route altitude, the minimum obstacle clearance altitude, and off-route obstruction clearance altitude. These altitudes are depicted on IFR en route charts and play an essential role in preventing terrain or obstacle collisions while ensuring the aircraft is within the proper navigational coverage. The minimum route altitude, or MEA, is the lowest altitude that guarantees both obstacle clearance and reliable signal reception from navigational aids along the route. It ensures that aircraft stay above all obstacles in the area, 1,000 feet in non-mountainous areas and 2,000 feet in mountainous terrain, while being able to receive the necessary navigational signals. The MEA is the preferred altitude for en route IFR operations as it guarantees both safety and navigational reliability. MEA values are displayed above the airway or route segment they apply to, is shown in thousands of feet and typically in large font. If there are different MEAs for one direction versus the other, they will be displayed side by side with directional arrows to clarify which applies. Then we have the minimum obstacle clearance altitude, or MOCA, that is the lowest altitude between two fixes that guarantees obstacle clearance, similar to the MEA. However, it has a limitation in terms of signal reception. The MOCA only ensures navigational signal coverage within a 22 nautical miles radius of the BOR or other navigate defines the route. While it guarantees obstacle clearance, it may not ensure the aircraft can receive the navigation signal for the entire route, especially when navigates are spaced far apart. MOCA is usually marked with an asterisk on IFR charts to differentiate it from MEA. MOCA values are displayed below the MEA value or nearby the route segment they apply to. Now, last but not least, we have the off-route obstruction clearance altitude, or OROCA, that is used primarily for flights that do not stay on defined airways or when flying off-route. It is the minimum altitude that guarantees obstacle clearance within a given area, typically 100 nautical miles radius from a navigational fix. The OROCA provides the necessary clearance from terrain and obstacles but does not guarantee navigational signal reception or communications coverage. It is essential for planning when an aircraft deviates from airways. OROCA is displayed in a quadrangle of the chart bounded by latitude and longitude lines. The OROCA value is shown in large bold numbers indicating the minimum altitude in thousands and hundreds of feet. And it does not apply to a specific route, but instead provides an obstacle clearance for all airspace within the quadrangle. Now let's talk about waypoints, and fixes. These are critical elements of IFR and route charts, providing precise navigation points for pilots to follow. What are fixes? A fix is a specific geographic position determined by navigation aids, intersection of radials, or coordinates. Fixes are used for position reporting, defining intersections between airways, and determining altitude changes or turns along the route. A waypoint is a specific location defined by latitude and longitude coordinates. Unlike fixes, waypoints are often independent of traditional ground-based navigational aids. They are used in RNAV procedures to define airways or GPS-based routes, enable direct routing, and support advanced navigation systems like RNP. Now, how are they represented on the IFR en route chart? First, we have to know what is a fixed compulsory and a not compulsory position report. A compulsory fix or waypoint is a designated location where pilots are required to report their position to ATC unless they are in radar contact. A compulsory fix is represented as a small black triangle, and each fix is labeled with a unique name, often 5 characters long, and have additional information such as altitude constraints or reporting requirements that may be included. RNAV compulsory waypoints are depicted as blue 4-point stars on IFR charts, distinguishing them from the traditional fixes. They also have a unique 5-character name. Now, a non-compulsory fix or waypoint is a navigation point where position reporting is optional unless ATC specifically requested. These are typically used in radar control environments where ATC can monitor aircraft directly. The fix is represented by a low black triangle, and the waypoint is represented as a blue hollow 4-point star. Now let's dive a little into some other IFR charts that are important for in-flight operations. Standard instrument departures are a published procedure that guide aircraft from the runway to the en route structure while ensuring obstacle clearance and streamlining traffic flow. For dispatchers are essential for choosing a departure route that aligns with airport constraints, weather, and aircraft performance. Also reducing complexity by coordinating predictable departure paths with ATC. Pilots benefit from these charts because they provide clear instructions for altitude, speed, and heading, reducing workload after takeoff. By following these charts, pilots can focus on managing the aircraft and communicating effectively with ATC. These charts simplify the departure phase, making it safer and more efficient for everyone involved. The standard terminal arrival routes STARS are pre-planned routes designed to transition aircraft from the en route phase to the terminal area in orderly manner. Dispatchers use these charts to plan arrivals that align with the expected approach and runway configuration, and manage traffic flow efficiently, especially in busy airspaces. For pilots, STARS help by providing a predictable descent path that minimizes ATC instructions and prepare them for the approach phase by aligning the aircraft with the selected runway. STARS ensure smooth and controlled arrivals, reducing the risk of delays or confusion. Last but not least, we have the instrument approach procedures. These provide detailed information for descending and aligning with the runway, particularly in low visibility conditions. Dispatchers select appropriate instrument approach procedures based on weather conditions, runway availability, and aircraft equipment capabilities. Ensuring suitable instrument approach procedures are available at alternate airports in case of diversion. Pilots rely on instrument approach procedures for safe navigation during the critical approach and landing phase, ensuring obstacle clearance, and executing precision or non-precision approaches depending on the conditions and airport infrastructure. These are essential for safe landings, particularly when weather or terrain challenge visibility. Now I will guide you through an example of planning a flight using IFR charts, in which we will explore each phase of the flight, departure and route, arrival and approach, highlighting the critical decisions and the reasons behind them. Step 1 is the pre-flight preparation, in which we will check weather and NOTAMs to be aware of any airspace restriction, navigate interruption, or airport-specific issues that could affect the flight. Step 2 is selecting the appropriate SID. The SID connects the departure runway to the en route airways in a standardized and predictable manner. Why we choose a specific standard instrument departure? Because of the runway assignment, the SID must align with the departure runway. Also, traffic flow. Air traffic control uses SIDs to manage traffic efficiently, minimizing conflicts. And the transition point. A good SID leads smoothly into the en route structure, reducing workload. For example, if the SID includes altitude restriction, we ensure that these are manageable based on the aircraft performance and any airspace constraints. Step 3, we plan the en route phase. The en route phase connects the departure and arrival points via airways or direct routing. We use IFR en route chart to plan this portion of the flight. Critical considerations: airway selection. Airways provide a defined path between waypoints or navates. We select airways that minimize fuel burn and distance while avoiding restricted areas or significant weather. Cruising altitude. The chosen altitude depends on the aircraft performance, direction of flight, odd or even altitudes, and forecast winds aloft. We also consider factors like turbulence and icing at certain altitudes. Navigate and RNAV coverage. For conventional navigation, we ensure consistent navigate coverage along the route, and for RNAV-capable aircraft, we confirm the availability of GPS waypoints. Step 4. Selecting the STAR, or Standard Terminal Arrival Route. As we are near our destination, the STAR transitions us from the en route airways into the terminal area. STARs simplify arrivals, ensuring safe and orderly traffic flow. Why we choose a specific STAR? Because of the arrival direction. The STAR must align with the direction of approach to the destination airport. Also, the altitude and speed restrictions. These are critical for sequencing with other aircraft. We must verify the aircraft can meet these restrictions. And the runway assignment. If a star leads to multiple runways, we ensure our planned runway matches the star's path. Stars often include crossing restrictions at specific waypoints, which we will note to prepare for decent planning. Step 5. Selecting the instrument approach procedure. This guides us from the terminal area to the runway, ensuring safe and stable descent. Factors in choosing the instrument approach. Weather conditions. If the weather is clear, we might opt for a visual approach, but in low visibility, we select an ILS or RNAV approach for precision. Aircraft equipment. The aircraft navigation system dictates which approaches are available. For example, an aircraft without GPS cannot perform an RNAV approach. Runway assignment. The chosen instrument approach must match the anticipated landing runway. Planning a flight under IFR conditions is a detailed process that requires careful consideration of SIDs and route charts, stars, and instrument approach procedures. Each decision from departure to approach is made to ensure safety, efficiency, and compliance with ATC instruction. By understanding these procedures, we are not only enhance our situational awareness. IFR route optimization involves selecting the most efficient flight path between departure and destination while complying with regulatory and operational constraints. It aims to reduce fuel consumption, flight time, and operational costs while ensuring safety and adherence to air traffic control regulations. Efficient routes minimize unnecessary deviations, reduce environmental impact, and enhance airline profitability. Now let's see some factors affecting route selection. Wind conditions. High altitude winds like the jet stream can be advantageous if they align with the flight direction tailwinds, significantly reducing fuel burn and flight time. Conversely, strong headwinds can increase resistance, requiring route adjustments. Also, crosswinds this affect stability and fuel efficiency, especially during approach and departure, prompting consideration in route selection. Air traffic control restriction. To manage airspace capacity, ATC may impose delays or reroute traffic to prevent congestion. These adjustments often prioritize safety but can affect efficiency. Also, ATC assigns predefined airways for IFR flights, limiting flexibility in direct routing. Innovations like user preferred routes allow airlines to suggest optimized paths subject to ATC approval. Airspace structure. Routes often depend on ground-based navaids like VORs or RNAV waypoints. Transition to performance-based navigation expands routing flexibility in less equipped areas. Weather, convective activity, thunderstorm, turbulence, or hail conditions are avoided by choosing alternative routing. Real-time updates help pilots and dispatchers adjust the route in flight. Also, at specific altitudes, pilots may need to climb or descend to avoid hazardous icing layers, impacting the efficiency of the chosen route. Aircraft performance. Aircraft perform most efficiently at certain altitudes. Wind, weight, and airspace constraints may force deviations. Also, flights must balance fuel capacity with alternate route planning for emergencies. Tools and techniques for IFR route optimization. Flight planning software. These programs automate and optimize route planning by integrating data such as weather, airspace restrictions, aircraft performance, and ATC regulations. Calculate the most fuel efficient route, account for real-time weather updates, and provide alternate routes in case of unforeseen changes. Some example will be Jepson JetPlan, widely used by airlines for optimizing long-haul and short-haul flights. Lido Flight 4D provides advanced route optimization based on weather and airspace management. And ForeFlight, popular among general aviation pilots for ease of use and real-time data integration. Aircraft monitoring systems like the flight management system on board aircraft continuously monitor and optimize the flight path in real time. It adjusts altitudes and speed based on changing conditions like wind or ATC instructions, and provide alerts about deviations from optimal performance. Perform-based navigation. PNB allows for greater flexibility in route design by enabling aircraft to navigate using satellite systems rather than fixed ground-based aids. These enable direct routes, reducing distance and fuel consumption, and improve access to airspace with fewer restrictions. Let's see a real-world application of IFR route optimization. Delta Airlines face a common challenge in Trans-Pacific operations. They need to balance efficiency, fuel cost, and operational constraints while traversing vast distances with dynamic weather conditions. Their solution was to adopt an advanced route optimization strategy, leveraging real-time data and innovative planning tools. By using predictive models, Delta analyzed wind patterns, including the Pacific jet streams, to adjust routes. Eastbound flights leverage strong tailwinds for reduced fuel burn, while westbound flights avoided headwinds, even if it meant deviating from traditional airways. The airline utilized advanced flight planning software integrated with real-time weather updates and aircraft performance metrics. This ensured that each flight plan was tailored to specific conditions on the day of operation. Instead of rigid adherence to fixed airways, Delta implemented user-preferred routes taking advantage of performance-based navigation capabilities for greater flexibility over the oceanic airspace. Coordination with ATC centers in oceanic airspace ensured compliance while allowing for more efficient routing when possible. Benefits that they had because of this optimization: fuel savings by avoiding headwinds and optimizing cruising altitudes. Delta saved approximately 1,100 kilograms of fuel per flight on average for westbound routes. Eastbound flights leveraging tailwinds saw time savings of 10 to 15 minutes per leg, allowing for improved scheduling and reduced crew duty times. These efficiencies translated into over 3 million in annual cost savings, demonstrating the financial benefits of robust route optimization. Fuel efficiency directly reduced Delta carbon footprint with an annual reduction of approximately 9,000 metric tons of carbon dioxide emissions, aligning with the airline's sustainability goals. This case highlights the transformative power of IFR route optimization in long-haul operations, serving as a model for other airlines looking to reduce costs, improve efficiency.
This is Denise speaking. I'm going to introduce what is weight and balance, human factors, and not high level. Starting with weight and balance principle of weight and balance. Weight and balance refer to the distribution of weight within aircraft and how it affects the aircraft stability and safety. Weight is a force exerted on the aircraft due to gravity, including all components such as passengers, cargo, fuel, and the aircraft structure itself. Balance refers to how this weight is distributed across the aircraft, particularly around a critical point known as the center of gravity. Proper weight distribution is crucial for maintaining aircraft stability, as an improperly balanced aircraft can result in control problems during flight. Continuing with the principle of weight and balance, we have the center of gravity, CG. It's the point in aircraft where its weight is evenly distributed in all directions. If the CG is located too far forward or too far aft, the aircraft may become difficult to control. If the CG is too forward, it can result in nose-heavy conditions. If the CG is too far off, it can lead to tail-heavy conditions. Moment. Moment is defined as a product of the weight of a particular component is distant from a reference point. So, moments are used to calculate the total moment of the aircraft, and the aircraft CG is derived by dividing the total moment by the total weight. This helps in determining how and where loads, such as passengers and cargo, should be distributed. Regulatory requirement Part 121. Part 121 of the Federal Aviation Regulations FAR governs the operation of domestic, flat, and supplemental operation by airlines. These regulations are specially designed to ensure that airline meets safety standards, including proper weight and balance procedures, to ensure safe and efficient flight operations. Documentation and procedures. Airlines are required to document the weight and balance information for every flight. This includes recording the weight of passenger cargo, fuel, and any other items on board. Compliance and inspections. The Federal Aviation Administration and other regulatory bodies enforce Part 121 complaints through regular audits and inspections. These inspections ensure that airlines are meeting safety standards, including adherence to weight and balance regulations. Non-compliance could lead to operational penalties, fines, or suspension of operations. So we have a paper-cutted weight and balance calculation sheets. We have the weight, hour, and the moment for each item listed on the left side. At the bottom, we have our envelope where we need to plot our total weight and center of gravity and ensure the intersection falls within the grid. If it falls outside the grid, it means the aircraft is outside the manufacturer limits, and we will need to readjust the load. Starting with the station, basic empty weight. This is the aircraft weight without any passengers, baggage, or usable fuel, but including hydraulic fluids and unusable fuel. Usable fuel. This is a fuel that can be used with a maximum of 48 pounds. Pilot and front seat pass. The combined weight of the pilot and the passenger in the front seat. Rear passenger. The weight of the passenger in the rear seat. Baggage area 1. This aircraft only have one baggage compartment, which is accounted for in baggage 1. So we have the baggage area 2. The earn is listed as 0 because there is no second baggage compartment. So it is not included in the calculation. Run weight. The total weight of the aircraft when it is on the ramp or parked. Taxi fuel. This is a standard adjustment provided by Piper, indicating a reduction of 7 pounds in weight and 665 units of movement during taxi. Take-off weight. This is calculated by subtracting the taxi fuel from the run weight, giving us the weight at takeoff. And road fuel. This is a fuel that will be burned during the flight. Landing weight. This is calculated by subtracting the en-route fuel from the takeoff weight. It is important to remember that each aircraft has its own weight. In the basic empty weight, we obtain the aircraft weight that is within the aircraft itself. The operations are obtained by multiplying the weight by the earn, and so on with all the operations we have in the table. Remember that in this example we use pounds, so we convert gallons to pounds to be able to perform our operation. In this case, we say that we only have the student structure, which is why the rear passenger box is blank. So it's the baggage area too. The run weight will be the sum of all the previous weight, and the moment will also be the sum of all the previous sums. And the earn will be obtained by dividing the moment by the aircraft weight. Taxi fuel is obtained from the information given to us by the aircraft POH. And road fuel is calculated with the amount of gallon we are going to burn multiplied by 6, and it will give us the weight. Finally, the landing weight is the subtraction of the takeoff weight and the road weight. With this, we conclude our explanation, noting that we are within the appropriate weight for the aircraft. Impact on aircraft performance, takeoff and landing. The aircraft CG directly impacts its takeoff and landing performance. A forward CG requires more force to lift the nose during takeoff, possibly increasing the distance required to become airborne. Commercially, aft CG can cause the aircraft nose to lift too quickly, which may result in a tail strike or difficulty in controlling the aircraft during takeoff or landing. Fuel consumption. Fuel efficiency is also impacted by the aircraft CG. When the CG is optimally positioned, the aircraft aerodynamic performance is improved, reducing draft and fuel consumption. Improper loading, on the other hand, can cause additional draft, leading to increased fuel burn. Stability and control risk. Aircraft with increased CG are at higher risk of becoming unstable, particularly in turbulence conditions. A nose-heavy aircraft is harder to maneuver because the pilot may struggle to raise the nose during takeoff or climb. A tail-heavy aircraft, meanwhile, is prone to instability, especially at higher altitudes or in turbulent air, making it harder for pilots to maintain control. Human factors. The term human factor has grown increasingly popular as the commercial aviation industry realizes that human error, rather than mechanical failure, underlies most aviation accidents and incidents. Human factor science or technologies are multidisciplinary fields incorporating contributions from psychology, engineering, industrial design, statistics, operation research, and anthropometry. It is a term that covers the science of understanding the properties of human capability, the applications of this understanding to the design, development, and deployment of systems and services, and the art of ensuring successful application of human factor principles into the maintenance working environment. Common human factors. Maintenance errors are parts installed incorrectly, missing parts, and necessary checks not being performed. In comparison to many other threats to aviation safety, the mistake of aviation maintenance technicians can be more difficult to detect. The list of human factors that can affect aviation maintenance and work performance is broad. Fatigue. Fatigue is a significant issue in aviation, affecting the ability of flight crews to make sound decisions. Long flights, irregular schedule, night shift, and jet lag contribute to fatigue, which can lead to slower reaction times, impaired judgment, and increasing risk of error. Communication breakdowns. Clear communication is paramount in aviation. Misunderstanding or lack of clarity in verbal communication, whether within pilots and air traffic control or within a flight crew, can lead to errors. Factors like language barriers, distraction, or assumption often contribute to communication breakdowns. Situational awareness. Situational awareness refers to a group's understanding of their environment, including factors like position, altitude, weather, and system status. Lack of situational awareness, such as misjudging altitude or approaching the wrong runway, can lead to incidents or accidents. Case study. In 1977, two Boeing 747s collided at Tenerife Airport due to miscommunication, poor decision-making, and a lack of situational awareness, resulting in 583 fatalities. Key human factors. Communication breakdown. The KLM captain misunderstood air traffic control instructions, leading to erroneous belief that takeoff clearance was granted. Decision-making under stress. The KLM captain facing time pressures due to duty limitations, attempted to take off without clearance. Lack of situational awareness. Dense fog obscured visibility, and neither group recognized that they were on a collision course. Lesson learned. Standard communication. Aviation language was clarified to reduce ambiguity. Crew resource management. CRM was introduced to improve crew cooperation and communication. Situational awareness technology. Ancient radar, TCAS, and EGPWS systems were implemented. Not high-level airspace. The North Atlantic high-level airspace is a design area of controlled airspace that handles a large volume of transatlantic flights, particularly between North America and Europe. It is vital for ensuring safe, efficient management of these flights, as radar coverage over the ocean is limited. Role in transatlantic flights. Not high-level airspace provide a structure for air traffic control to safely manage high-density traffic over Atlantic, maintaining separation sterling and ensuring safety where radar surveillance is minimal. Regulation and procedure. To maintain safety and order within not high-level airspace, a rigorous set of rules and procedures are in place. These regulations are primarily established by the International Civil Aviation Organization and implemented by regional bodies like the North Atlantic Regional Board, North Region. Separation standard. Aircraft operating within not high-level airspace must maintain specific distance from each other, both horizontally and vertically. These separation standards are calculated to ensure that aircraft have sufficient space to maneuver safely. Communication protocols. Efficiency communication is paramount in such a busy airspace. Pilots are required to maintain regular contact with air traffic controllers, providing updates on their position, altitude, and flight path. High frequency. Radio is the primary mode of communication in this region due to its long-range capability. Flight planning. Before entering not high-level airspace, pilots must submit detailed flight plans. These plans include the intent route, altitude, and estimate time of arrival. Air traffic controller use this plan to coordinate the movement of aircraft and prevent conflicts. Operational challenge. Oceanic clearance. Aircraft must obtain oceanic clearance before entering not high-level airspace. This clearance is essential for coordinating the flow of air traffic and preventing conflicts. Weather considerations. Weather conditions over the Atlantic, such as turbulence and jet streams, can impact flight planning. Pilots must account for these conditions to optimize fuel usage and minimize discomfort. Case study. JFK-to-LHR. Planning and execution. The flight crew of transatlantic flight from JFK to LHR planned efficiency route securing necessary oceanic clearance, factoring in weather conditions and ensuring sufficient fuel reserves. Key takeaways. Planning and adaptability. Successful flight planning and the ability to adapt to changing conditions were critical for a safe and efficient journey. Communication. Reliable communication with air traffic control ensure coordination in radar limit airspace. Situational awareness. Position reporting SB technologies exchange situational awareness, ensuring safety in the ascent of radar.
Hello, it's Geisen speaking, and now I'm going to talk about ETOPS, which stands for Extended Range Twin Engine Operational Performance Standards. This is a regulatory framework developed to allow twin-engine aircraft to fly routes that are beyond the traditional 60-minute range from an adequate airport in case of need. Initially, twin-engine aircraft could not fly more than 60 minutes from a suitable airport in case of engine failure. ETOPS standards have evolved, allowing extended distances, depending on the aircraft's certification, such as ETOPS 120 or ETOPS 180, and even up to ETOPS 330 in some cases. These numbers represent the maximum minutes that the aircraft can be from a suitable diversion airport in case of emergency. Introduced by ICAO and the FIA, ETOPS allows airlines to operate long-haul routes over remote regions like oceans or polar areas, expanding route possibilities and making operations more efficient for twin-engine aircraft, such as the Boeing 777 or Airbus A330. It benefits by reducing fuel costs, increasing flexibility in route planning, and reducing emissions due to more efficient aircraft and direct routes. Now, the regulatory requirements for ETOPS. First, flight planning. ETOPS regulations mandate higher fuel reserves for contingency planning. These reserves account for potential diversions to the farthest alternate airport on the planned route. This planning considers factors like headwinds, expected altitude, and the need for fuel to reach an alternate airport safely. Also, must consider high altitude fuel burn rates, descent fuel usage, and any expected headwinds. Airlines conducting ETOPS flights are subject to specific maintenance standards to ensure engine and system reliability. Engines on ETOPS certified aircraft undergo rigorous inspections and testing protocols to meet reliability standards. Airline must continuously monitor engine performance, track engine failures, and conduct regular reliability assessments to maintain ETOPS certifications. Then, the certification process. First, aircraft certification. Regulatory bodies like the FIA, the Federal Aviation Administration, and the EASA, the European Union Aviation Safety Agency, certify aircraft models for a specific ETOPS level, for example, ETOPS 120 or ETOPS 180. Each level specifies the maximum allowable diversion time from a suitable alternate airport. The aircraft must demonstrate high engine reliability over extensive testing, with dual engine failure incidents required to be extremely rare. This testing includes simulated single engine operations and operations in various conditions to prove both the aircraft and the engines can handle extended single engine flights. ETOPS certified aircraft must have redundant critical systems like hydraulic, electrical, and fire suppression systems, and backup power sources. These are crucial for operating safely on a single engine over long distances. Aircraft used in ETOPS operations must be equipped with real-time monitoring systems that allow continuous tracking of engine and system performance. This ensures the crew can detect and address any irregularities promptly. And second, the operator certification. In here, airlines must apply for ETOPS certification, which is separate from aircraft certification. This involves demonstrating to the regulatory authority that they have the necessary maintenance programs, crew training, and operational protocols in place to safely handle ETOPS flights. Certification includes audits, inspections, and the ability to maintain engine reliability records. And then the alternate airports. For each ETOPS flight, airlines must designate alternate airports that meet a specific operational and regulatory criteria within the ETOPS certified time limit. Suitable alternate airports must be available through the planned route and accessible in case of an emergency diversion. This airport must have adequate facilities and runways to accommodate the specific aircraft type. With runways that meet the aircraft performance requirements, The airport must also have fuel services, fire and rescue operations, and maintenance facilities, if it's possible. The airline must ensure that these airports can handle the passenger and logistical needs of all a diverted ATOPS flights, including medical assistance, refueling capabilities, and passenger accommodations if necessary. We also have some operational considerations. First, extended fuel reserves. ETOPS regulations require additional fuel reserves to account for potential diversions. These reserves include the diversion fuel. This fuel is to fly to the most distant alternate airport in the event of an engine failure or another emergency. Then the hold fuel. This is an additional fuel to account for potential holding patterns or delays at the alternate airport. And the fuel for weather and operational variability. This is accounting for factors such as high altitude winds, possible headwinds, and atmospheric conditions that could affect fuel consumption. Since ETOPS operations require aircraft to be able to fly to an alternate on one engine, dispatchers consider single engine performance and fuel efficiency. They may adjust fuel calculations based on the expected performance of a single engine cruise. Second, the emergency procedures. In the event of an engine failure, ETOPS trained pilots follow a specific set of procedures to stabilize the aircraft and assess the best diversion options. These protocols include identifying the nearest alternate. Using the real-time location and navigation data, the flight crew identifies the nearest ATOPS alternate that meets weather and operational standards. Then, coordinating with ATC and dispatch. The flight crew works with air traffic control, the ATC, and dispatch to ensure safe routing to the diversion airport, including adjustments for altitude and descent planning. And third, passenger and crew management. ETOPS emergency protocols include specific procedures for handling onboard situations, such as communicating with passengers, managing in-flight service interruptions, and preparing for a possible emergency landing. ETOPS training prepares pilots and crew for extended range flight operations over remote areas, and this training includes the emergency decision making, that are simulations and drills that prepare crews to make quick, informed decisions in response to in-flight emergency. Now, the contingency planning for remote operations. First, the route-specific considerations. ETO flights, particularly those over oceanic or polar regions, must consider additional factors like communication gaps and weather patterns and cold weather operations. First, the communication gaps. Some remote areas have limited communication coverage. ETOPS planning includes checking for radio frequencies or satellite communication links to ensure constant contact with ATC, and weather pattern and cold weather operations. Routes over polar or high altitude regions may encounter extreme weather, which can impact fuel burn rates, emergency descent planning, and the availability of alternates. Special attention is given to seasonal weather patterns, icing potential, and airport closures due to snow or extreme cold. And the medical passenger considerations. In the event of a diversion, ETOPS protocols cover passenger needs, from medical emergencies to accommodations if an extended layover at a remote airport is required. Crew training includes basic medical response and alternate airport selection, consider facilities for passenger care.
Now I'm gonna explain to you guys a case study about ETOPS.
For a case study, let's analyze a typical ETOPS operation for an airline flying a twin-engine Boeing 787 from Los Angeles to Tokyo Narita under ETOPS 180. Remember, ETOPS 180 means that an aircraft is certified to fly routes that take it up to 180 minutes. That means 3 hours of flying time away from the nearest suitable alternate airport. First, the route and flight planning. ETOPS 180 certification. Since this 10-hour trans-Pacific route crosses vast oceanic regions, it requires ETOPS 180 certifications, which means the aircraft must stay within 180 minutes of a suitable diversion airport. Then the selections of ETOPS alternates. The airline's dispatch team identified alternates within the route, such as Anchorage and Midway Atoll. These alternates are chosen based on runway length, operational readiness, and weather forecast. Then, the weather forecasting for diversion airports. Prior to departure, the dispatch team analyzes the weather forecast at each alternate. For instance, Anchorage must have clear visibility and no runway closures. If the weather is below ETOPS minimums, an alternate route or different alternates must be chosen. Second, the fuel planning. The ETOPS fuel reserves. Dispatchers calculate the required fuel, including diversion fuel for the farthest alternate, that is Midway Atoll, hold fuel for potential delays, and reserve fuel in case of unexpected conditions. Single engine performance. Since ETOPS operations require aircraft to be able to divert on a single engine, fuel calculations are adjusted for single engine flight, accounting for lower cruise altitudes and possible higher fuel burn rates. Contingency planning. Additional fuel is added as a contingency buffer for unexpected headwinds, potential holding patterns, or reroutes due to the weather at the destination of or alternates. And third, the pre-flight maintenance and reliability checks. The enhanced pre-flight inspection. The Boeing 787 undergoes through inspection focused on engine reliability and system redundancy, with particular attention to hydraulic, electrical, and fire suppression systems. Then the real-time engine health monitoring. As a certified ETOPS flight, the 787 is equipped with monitoring systems that continuously report engine performance and systems status to ground support. Any anomalies detected in pre-flight maintenance must be resolved before departure. Now, the in-flight monitoring and decision making. First, constant position and weather monitoring. In here, through the flight, the crew and dispatch center monitor the aircraft's position and update weather conditions at alternates. If a weather change makes an alternate airport unsuitable because of, for example, low visibility at Midway, the flight crew evaluates remaining alternates and adjusts the route if needed. Then the communication with dispatch and ATC. The crew maintains regular communication with both ATC and the airline dispatcher center, receiving updates on potential alternates and any real-time weather changes along the route. Fifth, the simulated in-flight emergency decision in just an hypothetical scenario. Engine malfunction over the Pacific, for example. Midway through the route, the flight crew detects a significant decrease in one engine's performance. Following ETOPS protocols, they begin a controlled descent and assess the nearest alternate. Then, also, decision to divert to Anchoras. Based on proximity and updated weather data, the crew selects Anchorage and as the diversion airport. They coordinate with ATC to establish a direct course to Anchoras, adjusting speed and altitude to optimize single-engine fuel efficiency. And onboard communication and preparation. In this case, the crew informs passengers of the situations, manages in-flight services, and prepares for a potential emergency landing upon arrival at Anchorage. Ground teams are alerted to arrange for refueling and passenger accommodations. In this case, we can mention some key operational takeaways from this ETOPS operation. For example, the pre-flight planning and alternates. Detailed route planning, fuel reserves, and alternate selection are crucial to ETOPS compliance and passenger safety. Also, the real-time monitoring and communication. In this, continuous monitoring of engine performance and weather conditions enables rapid, data-informed decision. Also, the crew training and preparedness. The crew's response to in-flight emergencies, including communication, fuel management, and passenger handling, highlights the importance of ETOPS-specific training. In ETOPS operations, key planning and operational decisions are essential to ensuring safety, compliance, and efficiency on long-haul routes over remote areas. These processes underscore the critical role of ETOPS-specific training and protocols which empowers airlines to manage long-range flights effectively, while maintaining the highest safety standards. Now let's talk about IFR planning application. IFR flight planning is the process of preparing a flight route that will be conducted under instrument flight rules, where the aircraft relies on instruments for navigation and control instead of visual cues. This is essential for flying in conditions of reduced visibility or in controlled airspace. The process ensures that the flight complies with aviation regulations, maximizes safety, and optimizes operational efficiency. IFR planning is essential for flying in conditions of reduced visibility or in controlled airspace. It carefully considers all the key factors needed to make a flight safe and efficient. For example, a properly planned IFR route prevents collisions by ensuring separation from other aircraft through the use of established airways and coordination with ATC. Also, planning identified suitable alternate airports and calculates fuel reserves, ensuring that the flight can divert safely in case of emergencies like engine failures or unexpected weather conditions. Efficient IFR planning minimizes fuel consumption by optimizing routes, altitudes, and airspeed, saving costs and reducing environmental impact. And then, by integrating real-time weather data, IFR planning avoids turbulence, thunderstorms, and icing conditions, enhancing passengers and crew safety. IFR flight planning is a cornerstone of modern aviation operations, balancing the twin priorities of safety and efficiency. By addressing navigation, weather, air traffic, and regulatory factors, it ensures that every flight operates within a structured and predictable framework, minimizing risk while optimizing resources. We also must take into account some considerations, like for example, route selection, airways and navigational aids. In this, under IFR, aircraft follow set airways or routes, like highways in the sky, called nav aids, such as boards that are very high frequency omnidirectional range, DMEs that are distance measuring equipment, and GPS waypoints, ensuring reliable navigation. These routes are carefully designed to keep aircraft safely separated and controlled, especially in busy or complex airspace. Following designated airways simplifies communication with air traffic control and ensures that the aircraft stays within regulated paths. Now, the alternate airports. In AFR planning, it's essential to identify alternate airports along the route. These are airports where the flight could land if it cannot reach its original destination, often due to bad weather, mechanical issues, or other unforeseen circumstances. Alternate airports are chosen based on their distance from the main route, runway availability, and the current and forecasted weather. Second, weather. Since IFR flights operate in a broader range of conditions than visual flights, dispatchers review weather reports for the entire route. This includes checking meters, that are the hourly weather observations, and TAFs, the terminal aerodrome forecast, and other data for temperature, wind, visibility, and conditions like fog, thunderstorms that may impact visibility and flight safety. Then, the weather influences the flight path and fuel requirements. Strong winds, for example, can speed up or slow down the aircraft, while adverse conditions like thunderstorms or icing zones, where ice can form on the plane, may require rerouting. Plannings consider conditions at the departure airport, the destination, and any alternates. For instance, a thunderstorm at the destination may make it unsafe for landing. So, dispatchers choose nearby alternates with clearer weather. This allows the flight to land safely even if conditions worsen en route. Third, the NOTAMs. NOTAMs provide essential time-sensitive information that might impact flight planning. These notices cover a wide range of updates, such as closed runways, restricted airspace, or construction at an airport. For example, if a NOTAM indicates that a runway at the destination airport is closed due to military activity, the flight plan may need to include a different runway or, in some cases, consider an alternate airport. NOTAMs also provide important route-specific information, such as temporary military training zones, hazards like obstacles near an airport, or even airspace restrictions due to special events. Reviewing these notices helps ensure that the flight can proceed without unexpected delays or detours. And last but not least, aircraft performance. Understanding the aircraft performance limitations is essential in IFR planning. This includes the aircraft maximum range, fuel consumption rate, cruising speed, and ideal altitude. IFR flights require enough fuel not only to reach the destination but also to divert to an alternate if necessary. Plus are reserved for additional time in the air. Factors like altitude, weather, and single-engine performance for twin-engine flights are considered, especially when flying over oceans or mountainous regions. About weight and balance, proper loading of the aircraft affects its performance, especially during takeoff and landing. The weight distribution in the cabin, cargo holds, and fuel tanks determines how well the aircraft can climb, cruise, and descend, which is particularly important in poor weather conditions or during long-haul flights. Ensuring optimal balance also contributes to fuel efficiency, which is essential in IFR planning. Each aircraft has specific performance limits for speed, altitude, and the ability to handle certain weather. For example, some aircraft may have lower tolerance for icing conditions or require higher cruising altitudes to avoid turbulence. Dispatchers consider these limits and select a route, altitude, and alternates that align with the aircraft's capabilities. Together, these factors ensure a well-prepared IFR flight, minimizing risk and enhancing the ability to handle any unexpected change in route. Now let's talk about tools and software. The complexity of IFR flight planning requires advanced tools and software to ensure safe, efficient, and compliant operations. These systems integrate vast amounts of data such as weather forecast, air traffic information, aircraft performance, and regulatory requirements into a cohesive plan. First, the flight planning systems. Comprehensive software solutions. IFR planning is streamlined with specialized software, such as Geisen Flight Deck, ForeFlight, and SkyVector, which handle route creation, weather data integration, fuel calculations, and airspace analysis. These tools help dispatchers and pilots design an efficient, compliant route while considering weather, airspace restrictions, and aircraft performance. Electronic flybags, EFBs. EFBs like ForeFlight or Garmin Pilot are digital systems that bring together charts, flight plans, weather data, and more into a tablet or onboard system. EFBs allows pilots to quickly access and update information mid-flight, improving situational awareness. With EFBs, pilots can track their position on navigation charts, monitor weather changes, and receive updated NOTAMs in real time. Also, flight planning software also includes fuel calculators that help determine the precise amount of fuel needed based on route distance, altitude, wind patterns, and alternate airports. This improves both efficiency and compliance with regulations that mandate specific reserve fuel amounts. At second, we have dispatch tools. Flight Management Systems, FMS. The FMS on board the aircraft calculates the most efficient route based on real-time conditions, considering factors like air traffic, weather, and performance. The FMS also assists with navigation, communicating with ATC for clearances, and rerouting as needed. Dispatchers use this system data to refine plans and adjust fuel, speed, or altitude based on real-time developments. Computerized dispatch tools. Airline dispatch centers use tools like Sabre Dispatch Manager or ARINC Direct to manage multiple flights, ensuring each one is optimized for fuel efficiency, regulatory compliance, and safety. These tools integrate weather, forecast, NOTAMs, and flight paths, giving dispatchers a full overview of current conditions and allowing them to communicate changes to pilots as needed. And then the weather integration platforms. Real-time weather services like Meteor Group Aviation or Weather Ops provide route-specific weather data. These platforms give dispatch and pilots continuous updates on turbulence, thunderstorms, and icing conditions, and more, allowing the flight to avoid hazardous weather and adapt if conditions change en route. Now we have an example of how we will apply everything to perform an IFR planning. Our point of departure will be Charlotte Douglas International Airport, KCLT. Our arrival point will be Phoenix International Airport, Sky Harbor, KPHX. First, we start by reading the NOTAMs and then we look up the meters for each airport used and for the alternates that we have chosen. Theoretically, the conditions of our alternate airport should be better than the one where we arrive to safeguard us from any weather event, emergency of another flight, and inconveniences. so that we are not in the middle of the flight looking for another alternate, since it would be annoying for the pilot. That's why the dispatcher helped with this task. We have calm winds of 10 miles at our departure airport, ensuring a smooth takeoff. We choose the departure procedure chart that will be BOPSI 5. With this, we know the runway and the airport information. We will use runway 36C as it is the longest runway, and it ensures that we will not have to deal with wind interference. At third, we choose the top of climb, or transition point, which will be BNA, that is the Nashville Vortac. Then we will head for Airways Quebec 34, with a heading of 253. Then we intercept Wacol with a heading of 253. We do the same with each en route section, based on the weather conditions in each area. Followed from Wacol to Ditzel, then intercept Trove with direct route to Airway Quebec 66. Then, here we will head towards Riggs and then Sifki, following the Airways Quebec 66. From Sifki, we will take a direct path to Pyramid, which allows us to avoid busier airports. Then we proceed to Ibeik and Siles. With these waypoints, we head directly to Evite, which will be our last segment before arriving to Sun, the transition point for our arrival procedure. Arriving at Sun, we will start the procedure we chose, the Jazz Tree, to our destiny. We choose the route based on favorable weather and visibility. Then we intercept runway 26, which goes according to the wind conditions. We design this route for efficiency, avoiding congested airspace while minimizing fuel consumption. By using Airways Quebec 34 and Quebec 66 with direct routes between crucial waypoints, we ensure a smooth and fuel-efficient flight while following the necessary procedures. The interconnection of all these topics ensures that airlines operate within a structured and resilient framework. By integrating regulatory compliance, real-time data analysis, and advanced planning techniques, airlines can maintain high safety standards while optimizing cost, reducing delays, and enhancing passenger confidence. When these elements are aligned, they form a comprehensive operational strategy that allows airlines to adapt to challenges effectively while meeting their operational and regulatory objectives. For example, in the regulatory foundation provides the legal and operational framework for airline operations, emphasizing safety and compliance. Real-world cases demonstrate the consequences of non-compliance and the importance of adhering to regulations. The meteorology applications highlight the significance of weather and flight safety, detailing tools such as METARs and TAFs in real-life scenarios, where accurate weather analysis was crucial. In MEL, CDL, and performance, we discuss how inoperative equipment and deviations affect performance, emphasizing decision-making based on safety and efficiency. In NOTAMs, we explain the role of the NOTAMs and the structure of the NAS, emphasizing their integration into operational planning for situational awareness. The IFR chart application guides the use of IFR charts for navigation, approach, and departure, tying into flight planning and execution. The route optimization in IFR planning covers strategies to save fuel and time while maintaining safety, showing how tools and technologies optimize routes. In weight and balance, we demonstrate how improper calculations can jeopardize safety, with examples of impact on performance. The human factors focused on the role of human behavior and decision-making and safety, offering mitigation strategies like the CRM. The specialized topics like the NAD, HLA, and the ETOPS explored advanced operational environments, challenges, and regulatory requirements, using case studies to provide practical insights. In the practical applications, with the IFR flight planning, ties all these elements together, illustrating how each topic integrates into a cohesive operational framework. Now let's do a case study. This case study examines an international flight from Miami International Airport, MIA, to Sao Paulo Guarulhos International Airport, GRU, showcasing the integration of these various operational elements and how they contribute to a safe and efficient flight. First, we have the pre-flight preparation. Regulatory compliance, the 14 CFR Part 121. This example, XYZ Airlines, operates under Part 121 regulations, which govern scheduled commercial air transport. These regulations ensure crew training, aircraft maintenance, and operational control meet strict standards. For this flight, the captain and first officer were certified for international operations, including oceanic navigation. Maintenance inspections were up to date, and dispatch verified operational compliance with South American aviation standards. This ensured safety and legal adherence for these international operations. Then meteorology applications. Meteorological data was critical to planning this route. METARs and TAFs provided real-time and forecasted weather for MIA, GRU, and alternates Galileo and Confins, the ones that we selected. The Intertropical Convergence Zone, ITCC, presented potential challenges with thunderstorms and wind shear. Jetstream's analysis suggested minor tailwinds that could reduce fuel consumption. This information shaped route decisions and contingency planning. With this, we can identify risks and opportunities, influencing route and fuel planning. Weight and balance. The passenger, baggage, and cargo loads were carefully distributed to maintain the aircraft's center of gravity within limits. This ensures optimal handling and stability during all phases of flight. The fuel load includes reserves for deviation and alternates, balancing safety and efficiency. Weight and balance checks are critical for takeoff and route performance and landing. The NOTAMs and NAS integration. We reviewed NOTAMs and revealed construction and GRU affecting taxiway usage. Additional, temporary restricted airspace near MIA required a modified Standard Instrument Departure (SID). Coordination with ATC allowed for an optimized clearance, ensuring no delays during departure. So NOTAMs informed adjustments to departure and arrival procedures, avoiding operational disruptions. And then the MEL and CDL. The MEL permitted operations with one inoperative lavatory, as it did not impact critical safety system. This ensured the aircraft remained airworthy without delaying the flight. So MEL considerations enabled the flight to operate efficiently despite minor equipment issues. Now the flight planning. First, we have the IFR flight planning. The planned route followed South Atlantic Airways, with alternate airports selected based on fuel and weather criteria. This will be Galileo and Confins. The star for GRU considered visibility and traffic congestion. Detailed planning reduced in-flight decision-making and enhanced operational predictability. In few words, IFR planning optimizes safety and efficiency, integrating weather and regulatory requirements. Second, we have route optimization. Adjustments were made to avoid turbulence or delays near the ITCC. By coordinating with ATC, the flight diverted slightly south while maintaining optimal fuel consumption. Step climbs based on weight reductions ensured further efficiency. So, route optimization minimized weather impacts and reduced operating costs. And then the IFR charts. And route charts were used to navigate through Caribbean and South American space, ensuring compliance with altitude constraints and airways requirements. Terminal charts for crew prepared the crew for a smooth air nav approach amidst traffic. So, IFR charts provided essential guidance for navigation and approach, ensuring accuracy and compliance. Now, in flight operations. First, we have the human factors. Crew fatigue management was critical for this overnight flight. Rest periods per pilots were scheduled per Part 121 guidelines. CRM, crew resource management, ensured effective communication during deviations around thunderstorms. So human factors management enhanced safety and efficiency during the operations. Now the meteorological adjustments. The ITCC required deviations 40 nautical miles south of the planned route. ATC was notified early, ensuring a smooth transition back to the airway. This proactive approach avoided severe turbulence and maintained passenger comfort. In-flight weather adjustments demonstrated flexibility and prioritization of safety. Now ETOPS and alternate planning. While not a traditional ETOPS route, the operation followed similar standards for alternate planning. Galileo and confines were monitored for weather suitability through the flight, with sufficient fuel reserved for diversion if necessary. Weight and balance. Fuel burn during the flight shift weight distribution. Systems continuously monitor the center of gravity to ensure stability during descent and landing. Then the arrival and post-flight. First, landing at Gru. The aircraft performed a smooth air-nav approach due to traffic at Gru. Tailwinds necessitated a slight adjustment in a descent speed to maintain sequence in the star. Construction-related taxiway closures required ground control coordination for efficient taxiing to the gate. So, landing operations were adapted to local conditions, ensuring safety and minimizing delays. And then the post-flight review. Dispatch reviewed meteorological deviations and fuel usage for future route planning improvements. The crew provided feedback on CRM and operational challenges encountered during the flight. And the post-flight analysis identified areas for future optimization and operational learning. This case study demonstrates how each topic is interconnected. Regulatory compliance forms the foundation for safe operations. The meteorology and NOTAMs guide route and contingency planning. Weight and balance and MEL CDL ensure operational efficiency and airworthiness. Human factors and CRM mitigate risks during in-flight decision making. IFR tools and route optimization enhance navigation and cost efficiency. Post-flight review fits back into the cycle of improvement. By integrating these elements, Airline executed a safe, efficient, and regulatory compliant flight from MIA to GRU.
Conclusion. This project has developed into a wide range of critical aspects of airlines operations, from regulatory compliance to technological advancements. We have explored the intricate detail of 14 CFR Part 121 regulations, the influence of meteorology on flight planning, and the importance of MEL, CDL, and performance considerations. We have also examined the role of NOTAMs and the NAS, the intricacies of AFR chart application and route optimization, and the fundamental principle of weight and balance. Additionally, we have discussed the impact of human factor on aviation safety, the unique challenge of not high-level airspace and ETOPS operation, and the practical application of EFR flight planning. It is evident that a holistic approach to airline operation is essential for ensuring safety, efficiency, and profitability. Each element we have discussed in interconnect failure in one area can have cascading effects on others. A comprehensive understanding of regulatory requirements, meteorological conditions, aircraft performance, and human factors is crucial for effective decision-making and risk mitigation. As the aviation industry continues to grow, it is imperative to prioritize safety, sustainability, and efficiency. By embracing a holistic approach and staying abreast of emerging trends, airlines can position themselves for success in the years to come.